Today's lesson is on analyzing graphs and functions. So to start with, there's a quick intro, which is just on domain and range. So why don't you work on those by yourself? The answers are posted on my website under the class notes tab. So starting off, we're just going to analyze graphs. Basically, this is just how to read a graph. So do you understand what the x-coordinate represents, and do you understand what the y-coordinate represents? So number 1 says consider the graph of the function and use the graph to estimate the value of the stock on the 10th day. And then we're told to confirm our answer algebraically. So to start off with, we want to think to ourselves, all right, when is the x value 10 and what is the corresponding y value? Right here is an x value of 10. Let's trace this line up to approximately right here. And then if we trace this line over to our corresponding y value, it would be at approximately 32. So think to yourself, okay, so what I just wrote here was that graphically on the 10th day, each share is approximately $32. And what I was doing is referring to the 10th day on the x-axis. Trace that up. It refers to a $32 share. Okay, read your x-axis info, read your y-axis info. All right, after we analyze the graph graphically, we need to confirm our answer algebraically. And confirming our answer algebraically would just be taking the function that's given, so this function down here, and substituting 10 in for your x values. We know our x value is 10. We're looking for the 10th day. So therefore, we substitute this into the function as f of 10. We have 0.002 times 10 to the 4th minus 0.11 times 10 to the 3rd plus 1.77 times 10 squared minus 8.6 times 10 plus 31. So we need to type that entire expression into the calculator, and we need to solve. Okay, so you can see from our calculator here that when we evaluate our function with the input value of 10 for the 10th day, our output is 32. So our approximation on the graph was accurate. For part B, I'm going to just point out how to approach this graphically, and then you can finish the rest of this by yourself and check your answer on my website. So part B says to use the graph to estimate the days during which the stock was valued at $30 per share. That means we need to come up to the graph. Right here is $30 per share. So right across this graph, where does the graph, so the blue line graph, intersect $30? And I would say it happens right here. So at day 0. Happens again right here, which is at approximately day 9. And again right here, which is at approximately day 15. So I just talked about what the answers are going to look like. You guys should write those down, confirm this algebraically. You need to confirm all 3 of those algebraically, and check your work on my website on the answer key. All right, number 2 is, again, just analyzing the graph, so understanding what the questions are asking and how to match it on the graph. There shouldn't be too much work with problems like this, literally just understanding what it's asking. So part A says to find f of -6. So this is saying when the x value is -6, what is the corresponding y value? Remember that the input value is always the x value. So I'm going to go over to the graph and I'm going to look for where x is equal to -6. On the graph, -6 would be right here. The corresponding y value, so where is there a point at x equals -6? And that point happens at -6, -3. So therefore, your answer, f of -6, is equal to the corresponding y value of -3. And that's your answer. Next question says, is f of 3 positive or negative? So once again, that number right there is your x value. That means when x is equal to 3 on the coordinate plane, is your answer positive or negative? So we're going to go over here, we're going to look at where, positive 3 is. All it's asking is the answer going to be a positive or a negative answer. Well, the corresponding y value is right here. That's obviously a positive y value. It's at approximately 3.8 maybe. I don't know. Pretty close to 4. But no matter what, it's a positive value. And if you're confused by that, this part of the number line, so starting at 0 going up, is heading towards positive numbers, and heading down is heading towards negative numbers. This point here is in the positive section. Number C, letter C, says for what numbers x is f of x equal to 0. So we're looking for all points where x is, or f of x is equal to 0, when the y value is 0. So I can see that the y value is 0 right here. The corresponding x value is at -3. Right there, the corresponding x value is at 6. And here, the corresponding x value is at 10. So for what numbers x is f of x equal to 0? We could say x is equal to -3. That's this first one. We could say x is equal to 5, second one. Or x is equal to 10, the third one. All right, and the last part says, how often does the line x equal 5 intersect the graph? Don't be confused by questions like this. It's a pretty simple question. So if we had a line drawn at x equals 5, which is right here, how many times does my green line intersect the graph? And I would say that it only intersects the graph at this one location. So your answer would be 1 time. All right, x and y intercepts. They are a point where a graph intersects or meets the x or y axis, and this is called an intercept. The graph of a function can have, this is important, the graph of a function can have 0, 1, or more x-intercepts, so basically infinitely many x-intercepts, while it can only have at most one y-intercept. If it had more than one y-intercept, then it would fail that vertical line test that we learned about in lesson 1. X-intercepts are where it crosses the x-axis, and y-intercepts are where the graph crosses the y-axis. So the y-intercept is always written as 0, y, because when you have a y-intercept, the x value always has to be 0. So a point where a graph intersects or meets the y-axis is called the y-intercept. The y-intercept occurs when x equals 0. A function can have at most one y-intercept. To calculate the y-intercept, you need to find f of 0. In other words, substitute 0 in for the equation and solve. Okay, the next example set says to use the graph to approximate the y-intercept, then find the y-intercept algebraically. So, looking at the graph, it appears that the y-intercept is about right here. If this graph is increasing by units of 1, I would say it's at about 1 1/3. So we're just approximating this, so we'll see how close we are. We're not really sure, but that's what we pulled off of the graph. If we were to actually calculate this, we would calculate it by using f of 0. That means wherever we see an x-coordinate in our original function, or this function here, we are going to replace that with 0. The numerator becomes -2 times 0 cubed plus 4 divided by 3. In the numerator, -2 times 0 is just 0, and we're left with 4 over 3. 4 over 3 is the point indicating the y-intercept, or in other words, we have a y-intercept at 0, 4 over 3, which is the same thing as 1 1/3. So our approximation, or what we guessed to begin with over here, is the same thing as the point we found algebraically. Now that might not always happen. Sometimes you might be a little bit off, and that's perfectly fine. Algebra is always the most accurate, but looking at a graph is helpful as well. Next we have x-intercepts. X-intercepts are also called zeros, and they can be called roots, all the same thing. X-intercepts are written with the x-coordinate first, followed by 0 for the y-coordinate. X-intercepts are a point on the graph where it intersects or meets the x-axis. The x-intercept of a graph occurs where y equals 0. And a function can have infinitely many x-intercepts. So to calculate the x-intercept algebraically, you need to set the function equal to 0 and solve for the independent variable, or solve for x. This is going to require you to factor most equations, so factor by GCF or factor the trinomial, however you have to do it, but usually you're going to have to factor. First example, we're going to check our answers, or I should say we're going to pull our answers from the graph, and then we're going to check them algebraically. Pulling our answers from the graph, looks like we have an x coordinate or an x-intercept at -3, approximately, and another one at like 2.5 maybe. So these are both guesses. We're going to check them algebraically. When we calculate this, we take the original function and we set it equal to 0. We have 2x squared plus x minus 15 equals 0. This problem requires us to factor. So factoring, the way I always teach factoring is the a times c method. We have our a value of 2, our c value of -15. So a times c is equal to -30. We need to think to ourselves, what two factors, so what times what, is equal to -30, but also adds to this middle coefficient of 1. So what times what equals 30, and the same two numbers that add together to equal 1. That would be 6 times -5 and 6 plus -5. We're going to use those two values and we're going to rewrite our expression. We're going to rewrite it as 2x squared. Instead of writing 1x, or just x, we're going to rewrite this as plus 6x minus 5x minus 15 equals 0. All we did at this point was rewrite that middle term that I have highlighted in green. Instead of writing it as x, we write it as 6x minus 5. After you do that, you group the first two terms and the second two terms. The first two terms has a GCF of 2x. Left over is x plus 3. The second group has a GCF of -5. Left over is x plus 3. This is equal to 0. Now we group them. Our greatest common factors are going to be the first group. Actually, you can write it in any order, but I'm writing them as the first group. And our common factor, those two that I just highlighted in that green color, they have to be the same. So our common factor, we write once. Once you get to this point, you set each factor equal to 0. 2x minus 5 equals 0. 2x equals 5, or x equals 5 over 2. X plus 3 equals 0, or x equals -3. Those are our x-intercepts. It's a good idea to write them as ordered pairs. So an ordered pair of 5 over 2, comma, 0, and -3, comma, 0. So those also match up with our approximation from the graph. 5 over 2 is the same thing as 2.5. And -3, 0 was our other guess. We calculated both of those. So our answers correspond with our approximation off the graph, which is good. Okay, so complete the on your own section by yourself. This time you're looking to find both the x and y intercepts, so use what we went over in the last two examples. These directions also tell you to state the domain and range. This is from the first and second lesson. The next part of analyzing graphs is talking about symmetry. Symmetry is when you have a graph that can be reflected over a certain line. So if we take a look at this orange, obviously that's not a graph, but just to get the basic idea. If I was to draw a line directly down the center, right here, approximately, and fold that orange in half, that orange peel in half, on top of itself, you know that both sides, both this side and this side, would overlap perfectly on each other. Also, we could draw a line here, have the same thing. We could draw a line here, same thing. So this orange peel has multiple lines of symmetry. Not all graphs have multiple lines of symmetry, but this is a good example of what symmetry is. So there's three different types of symmetric functions. There's symmetric functions with respect to the y-axis, just kidding, x-axis, symmetric with respect to the y-axis, and symmetric with respect to the origin. And they're exactly what they sound like. So it looks like you could flip it over the x-axis, flip it over the y-axis, or flip it over the origin. All right, if a graph is symmetric across the x-axis, that means for every point x comma y, so for every point here, there has to be a mirrored point at x comma negative y, directly down here. It looks like you flip it across the x-axis. If you're not given a graph and you're just given a function and it says algebraically determine if the function has any symmetry, in this case, you would replace the y value with negative y and confirm that it's an equivalent expression. Next, we have symmetry with respect to the y-axis. Once again, exactly like you think. It looks like you can flip the graph over the y-axis and it overlaps onto itself. If you have a point x comma y and the graph is symmetric across the y-axis, that means that your x-coordinate becomes negative. The y-coordinate stays the same. If you were confirming this algebraically, you would replace the x-coordinate with a negative x and confirm that it's an equivalent expression. And lastly, we have symmetric with respect to the origin. Symmetric with respect to the origin is when the graph flips across the line y equals x. It also appears like you rotate the graph 180 degrees, so you can think of it either way. All right, so for this graph, for every point x comma y, there's also a point negative x, negative y. So in this example, if you were trying to confirm algebraically, you would replace x with a negative x and y with a negative y and confirm an equivalent expression. Besides from the symmetry, so symmetry across the x-axis, y-axis, or the origin. There's a couple other names for functions, and I should say that being symmetric across the x-axis is actually not going to be a function. It does not pass the vertical line test. So even though there can be symmetry here, it's not an actual function. But symmetry with respect to the y-axis is called an even function. And symmetry with respect to the origin is called an odd function. Both of these will always pass the vertical line test. All right, if we are testing for symmetry, we want to look at the graph and see if we can match it with any of the symmetric properties that we went over above. So any of these graph properties. Number one, it looks to me like that graph is probably flipped across the origin. Looks like it could be rotated 180 degrees. Looks like it could be reflected across that line, y equals x. But definitely symmetric to the origin. All right, I'm also going to notice that there's a point right here, which is at 2, 2. And this point right here is at -2, -2. That follows this pattern. I also just realized that I drew this line incorrectly. All right, so now that we understand that the graph is symmetric across the origin, or at least that's what we think it is, we need to confirm this. And to confirm it, we are going to follow this rule. So we are going to replace x with the negative x, replace y with the negative y, and make sure that our function comes out to be equivalent. Our function is currently x times y equals 4. Replace x with the negative x, y times negative y. This is equal to 4. And simplify this as much as possible. The only thing I know I can simplify here is that multiplying two negative numbers is going to come out to a positive, so there's no need to write those negative signs, which is just x times y equals 4. Therefore, these are the same. Our starting point and our ending point are the same. This is symmetric to the origin. Number two. Number two, right away, to me, looks like it's symmetric across the line x equals 0, or I should say the y-axis. It looks like if I folded my paper in half on that yellow line, my graph would overlap. So scrolling up to look at my options, it looks like it's reflecting across the y-axis. That would be this one here. I can also tell that in this function, if I have a point at x comma y, I have the same point on the other side, but with a negative x variable. This point on our graph is at 2, comma 2. This point is at -2, comma 2. Graphically, this does pass the test for symmetric across the y-axis, but let's confirm this. To confirm it, we need to use this rule. We're going to replace x with negative x and make sure our answer comes out to be the same as the original. Our original is y equals negative x squared plus 6. I'm going to replace x with negative x, so I have negative times negative x squared plus 6. And if you remember, any number raised to the power of 2 is going to be a positive value. This is going to simplify to the negative sign. This negative sign does not go away. So negative x squared plus 6, which is the same as your starting point. This graph is symmetric with respect to the y-axis. All right, besides knowing that the first graph, number 1 in the example, is symmetric to the origin, we also know that this produces or is called an odd function. And number 2 is symmetric to the y-axis. We know this is called an even function. Just as a little extra note, also leading us into the next section. So, like I said, leading us into the next section, we have even and odd functions. So even functions are if the graph is symmetrical to the y-axis, that's what we just talked about. Odd functions are if it's symmetrical to the origin. I drew my line wrong on the last graph for the origin, but I'll draw it right on this one. So it's actually reflecting across that line that I just graphed there. If you fold your paper in half on that line, this part would overlap with this part. So from the chart above, or from the graphs we just looked at, recall that an even function algebraically can be determined if you replace x with negative x and confirm that the expression is the same, or it's an equivalent expression to what you started with. So you replace x with negative x and you prove that it comes out to be the same as what you started with.
And when I write equivalent expression, I'm referring to the original expression. So what you started with, like what the first expression was that you were given.
All right, if you recall that an odd function can algebraically be determined when you replace x with negative x and y with negative y. You then have to confirm that you have an equivalent expression. So the only thing here is you typically start with function notation. So just a quick side note, remember that f of x, or function notation, is the same thing as just using y. So if we're replacing x with negative x and y with a negative y, this little note is going to be helpful. So I wrote replace y with a negative y, but this is the same as f of x with negative f of x. Confirm an equivalent expression. Okay, I do have one thing to point out here. If you're testing algebraically to see if something is even or odd, instead of following both of these, so instead of doing this and confirming if that's true, and then doing this and confirming if that's true, you can kind of skip a step in here, and you can just replace x with negative x. Both of those are in, both directions have replace x with negative x. If you replace x with negative x and it comes out to be the same as the original expression, then you're in the even graph. If you replace x with negative x and it comes out to be the complete opposite of what you started with, then you're in the odd function section. So I'm going to do a few examples, just pay attention to what they look like. These just take practice as far as understanding even and odd and understanding how to algebraically find them. All right, if we look at the first example, hopefully everyone can tell that there's no symmetry on this graph. So it does pass the vertical line test. If I draw a vertical line, it would pass everywhere. But it does not have any line of reflection that is at all important to us. So if we were to flip this across the y-axis, it would not end up on itself. If we were to flip it across this line, it would not end up on itself. And really, that's all we care about. So we would say neither even or odd. And for number two is a function. We have f of x is equal to x to the fourth plus x squared plus 3. This function here obviously is algebraic, so I'm going to just replace x with negative x. Remember that set of directions is in both of these. Therefore, this becomes f of negative x equals negative x to the fourth plus negative x squared plus 3. Any number raised to an even power is going to simplify to a positive number. That happens in this first expression and the second expression. Therefore, negative x to the fourth, regardless what the number is, it's going to simplify to a positive value. So we can just write this as x to the fourth. Negative x squared, always going to simplify to just a positive number, so write it as x squared. We have plus 3 at the end. The original expression and our simplified expression, once we substituted negative x in, is the same. So the same expression would indicate that this is even. Okay, I'm going to scroll down and do number 4 in the on your own section, just so you can see what an odd function looks like. So for this function, it's obviously algebra. Therefore, we're going to substitute negative x in for x. That gives us negative x in the numerator divided by negative x squared minus 1 in the denominator. So the numerator cannot be simplified. We're just going to leave that as negative x. And the denominator, we have negative x squared. That can be simplified to just x squared plus 1. So because we have a numerator that has a negative sign, that means it just changed the entire fraction to a negative. Technically, that numerator fraction, or that numerator negative sign, can be written out front as negative and then x over x squared plus 1. So this here just made this entire expression a negative value. And making that a negative value, or multiplying it by this negative number, is going to tell us that that is an odd function. So check my website for the rest of this on your own section answers, or the on your own section answers. And also take a look at the practice, because there's quite a few examples like this in the practice.